Bismillahirrahmanirrahim. We start a new chapter in operating system and we'll discuss CPU scheduling. This is our new chapter. Earlier, we had discussed about user processes. What is a process? What different states are there which normally a process shows during its lifetime? Then the state transitions have been discussed in previous lecture. We also discussed that there are generally two types of processes. One are I/O bound processes in which I/O requests are more than CPU execution, and some processes are CPU bound. That means CPU execution is more as compared to I/O request. So we'll carry forward the discussion from there, and in today's lecture we'll discuss what is CPU scheduling, how CPU is scheduled among different processes. CPU is a resource, as you know, and generally a single CPU is provided to be shared among so many user processes. Now, how single CPU is being used by different number of processes, this is the discussion of today's lecture. The agenda items for today's lecture includes the following items. First, we need to revise or understand some basic concepts. These are the concepts which we had already discussed in previous lecture. So it's a sort of revision or recap of the previous concepts we had discussed earlier. Then we will be discussing the scheduling criteria. Now, since we are discussing CPU scheduling, so the criteria we'll be discussing are for the CPU scheduling. So this is the only resource we are going to discuss in this chapter. Further, more resources will be discussed in different more chapters. So how CPU should be scheduled among different processes, and what are the criteria that need to be fulfilled before CPU needs to be assigned to some process. We'll be discussing those criteria. And then we'll be discussing different scheduling algorithms. These are CPU scheduling algorithms. Different algorithms are there that will explain in what sequence processes should be assigned to CPU. So we'll be discussing with examples how processes going to execute on CPU one after another and in what sequence. So this is the discussion agenda of today's or this chapter. Let's proceed with the first topic, and we have to revise some basic concepts. These are the concepts we had already discussed earlier in previous chapters. So what are those fundamental concepts? We already know that maximum utilization of CPU can only be obtained with multiprogramming. In first chapter, when we were discussing different types of operating system, we discussed multi-programming system, in which I had explained that these are the latest form of operating systems which we currently use in our different type of electronic devices. I had also explained its structure. It's sort of like this, a RAM that stores more than one processes at the same time. So the top location is occupied by the operating system, and rest of the memory or rest of the RAM is divided among user processes. So processes are stored in RAM one after another in sequence like this. This shows multi-programming. More than one programs can reside in RAM at the same time. Before multi-programmed systems, there were batch systems. In batch system, only one process, only one user job used to reside in RAM. And in that cases, CPU used to be idle a lot. But the more multi-programming is being ensured in systems, the more CPU is getting busy. So CPU utilization or maximum CPU utilization can be ensured with this multi-programmed systems. So the more processes are in RAM, the more CPU will be busy and it will remain idle for very short time duration. I had already told you that 100% CPU utilization is still not achieved. Still CPU remains idle but for very short duration. But we had achieved maximum utilization of CPU with multi-programming or multi-programmed systems. Now, a process is divided in two cycles. A process has CPU cycle and I/O cycle. Sometimes a process requires CPU and sometimes it requires I/O devices. So it keeps on executing between these different devices. At time, it would execute on CPU, and when it would require user to interact with them, it will go to the input device. And when it will require to display results to the user, it will go to the output device. So a process has both the CPU and I/O cycles in it. CPU burst is distributed within the process lifecycle. The CPU is not provided to a process only once. Rather, it is provided in quantums, in short durations, in short time spans. It is given CPU once for short duration and then it goes back to wait for its turn again in RAM. Then it comes again, CPU executed on CPU, and then it may go to some I/O device. Then it goes back. This is the three-state model diagram, if you remember we had discussed in chapter 2. So CPU is not assigned once in a process lifecycle. It may happen that a small process is given CPU just once in its lifetime, but generally a process CPU burst is distributed over its lifespan. Now the distribution diagram is given in the next slide. Here you can see a process has a sequence of I/O and CPU cycles. So at a time it will either execute on CPU or it will be executing on some input-output device. Once it is executing on CPU, it cannot be executed on some other device. So when a process is having its CPU cycle, when CPU cycle is over, then it has to go to the I/O device where it either may require to wait, as I had already told you that there are device queues in previous chapter. Every device, every hardware in your system has a queue. So there if that device is already busy with some other process. So this process has to wait in that device queue for its turn. So that process, after completing its CPU burst, may then have to go to the IO device and may wait there for its turn. When IO is over, it then CPU cycle, its CPU burst then starts again. And once CPU burst is completed and it again requires interaction with the user, so then it has to go to the IO device again. Either it will require some input from user or it will require to show some result to the user. And then the CPU burst starts, and then it may again go to the IO devices. And this process goes on until the process completes its execution and goes to termination. So a process lifespan is a sequence of CPU cycles and IO cycles. CPU is not assigned once, though it may be possible that a small process which just requires execution on CPU without any user interaction or without requiring to display some results to user. That may be possible, but generally a process is a combination of both CPU and IO cycles. In some cases, as I had said in previous lecture, some of the processes are IO bound. That means they would be having very small CPU bursts and more IO demands. And some processes are CPU bound. That means they have longer duration to be spent on CPU and very shorter durations on IO devices. But still, CPU and IO cycles are alternating in sequence. Now, in previous lecture, we had discussed about CPU schedulers. If you remember, we discussed different types of schedulers, and we discussed 3 different types of schedulers: job scheduler or long-term scheduler, CPU scheduler or short-term scheduler. These are the 2 main types of schedulers, and there was one more which we had called as the mid-term scheduler. Now the CPU scheduler, also known as the short-term scheduler, which we had said what is the responsibility of short-term scheduler or CPU scheduler. It mainly selects from among the processes in memory. That means it mainly shuffles the processes within the RAM and selects the one that should be sent next to the CPU. So it selects from among the processes in RAM that are ready to execute as the processes in RAM are in ready state, and then allocates the CPU to one of them. This allocation of CPU is actually done by another function of operating system which we call as a dispatcher. If you remember the dispatching function we had discussed when we were discussing the 2-stage transition model. So the main function of CPU scheduler is to shuffle or to organize the RAM, to arrange the processes in such a sequence that which process should be sent to CPU first is placed at the top of the ready queue, and those processes which are to be executed later on CPU are then placed towards the tail of the ready queue. So mainly it shuffles the RAM. Now there are 2 types of scheduling. This CPU scheduler performs 2 types of scheduling activities. One type of scheduling is known as preemptive scheduling. In preemptive scheduling, a currently executing process is stopped. That means if a process is being executing on CPU, so CPU scheduler, if it is a preemptive type of scheduling, if it is following a preemptive type of scheduling, so CPU scheduler will stop that running process and assigns another process to CPU. That is known as interruption. It would interrupt the process, the running process, and takes CPU from it and assign it to some other process. While the other type of scheduling is non-preemptive. That means CPU scheduler does not have the capability to stop the running or executing process and take the CPU from it by force. In preemptive scheduling, it takes CPU from one process, from executing process by force, by stopping it in middle. While in non-preemptive, the process which is executing on CPU is led to complete its CPU cycle. So, CPU scheduler, or also known as short-term scheduler, is the one which mainly selects which process should be sent to CPU, so that process is placed at the top of the ready queue. So mainly it shuffles the RAM and organizes it in the order in which the more important processes which are to be executed early should be placed at the top of the ready queue, while those processes which are not as important are then placed at towards the tail of the ready queue. So it shows two types of scheduling of CPU, either preemptive. In preemptive scheduling, if a process is executing on CPU, so this CPU scheduler stops the execution of that process, takes CPU from it and assigns CPU to some other process. While in non-preemptive version, a process which is being executing on CPU, the CPU scheduler has no capability to stop it and take CPU from it. So this is two flavors of CPU scheduling. Now, what is dispatcher? As I just said, selection of processes or organization of RAM is being done by CPU scheduler or short-term scheduler. Now, what is dispatcher? Dispatcher basically is a function or a routine of operating system. What does dispatcher do? Dispatcher module, it is a module or a function that gives control of the CPU to the process which has been selected by the CPU scheduler or the short-term scheduler. So if you remember, we had drawn a two-state model, and there I had told you that between the ready and running state, when a process which is in ready state is given CPU, so this function is known as dispatching. Dispatching is only used when a process is being sent from ready to running state. So dispatching function is being performed by this module dispatcher. It gives control of the processor to the process. Which process? That particular process which has been selected by the CPU scheduler. So the process that is placed at the top of the ready queue is given control of the CPU. Now, who places that process at the top of the ready queue? This is the job of the short-term scheduler or the CPU scheduler. Now, what is dispatch latency? Dispatch latency means dispatch delay. So what sort of delay it is? Time it takes for the dispatcher to stop one process and start another process. During this, your CPU is idle. Since I said multiprogramming still has not removed or finished the idleness of processors. Still, we observe idleness in case of CPUs. Though it has been reduced a lot, but still the delays are observed. And this is the reason of those delays. Dispatch latency. The time when dispatcher stops one process on CPU and assigns CPU to some other process. So during that switching, stopping one process from CPU and assigning CPU to another process, during this switching activity, the CPU remains idle. So this is the dispatch latency or dispatch delay. During dispatching, stopping of one process and assigning CPU to another process. During this dispatching activity, CPU remains idle. So that's why it is known as dispatch latency. Latency means delay or idleness. So this is the idleness I was referring earlier, that still our systems observe delays in case of CPUs. Now the next topic that we are going to discuss are the criteria. We had revised the topics we had discussed in previous chapters. Now we are going to discuss what are the CPU scheduling criteria. On what criteria we need to assign CPU to one process and in what order. So what are the criteria? We are going to discuss that criteria next. These are the 5 different CPU scheduling criteria. That means we are going to discuss different scheduling algorithms next. So that means which algorithm is more appropriate to be assigned or to be selected for CPU. So the one which fulfills these 5 criteria is generally selected for CPU scheduling. We will be discussing different types of scheduling algorithms in the coming lecture. So among those so many algorithms, which one is more suitable? So the suitable one is the one which fulfills or which follows or which observes these 5 different criteria. What are these criteria? The first one says CPU utilization. That means we need to keep our CPU as much busy as possible. CPU utilization should be maximized. The more delays an algorithm shows, the more CPU utilization is reduced. That means CPU would remain more idle, which is quite expensive. So an algorithm which keeps CPU as much busy as possible, so that algorithm, that CPU scheduling algorithm is considered more efficient. The next criteria is throughput. What is now throughput? Number of processes that complete the execution per unit time is actually throughput. That means within a unit time selected, for example, within 2 milliseconds, how many processes have completed their execution on CPU. So that would be the throughput of your CPU. So if an algorithm ensures that within a defined unit time, more number of processes complete their execution, that means the throughput of that algorithm is better than others. So the more processes complete the execution in defined time, that means such algorithm is more efficient, or we generally say that our system is quite fast as it completes our task quite quickly. So throughput actually defines the efficiency of your system. The next criteria is the turnaround time. What is now turnaround time? It is the amount of time to execute a single process. So turnaround time is the amount of time it takes to execute a single process on CPU. So if your processor takes a lot of time to execute a single process, that means the algorithm being utilized for its scheduling is not quite effective. So the one we have to select an algorithm, that one which reduces the amount of time a particular process or a single process takes to complete its execution. So in throughput we too have taken collective number of processes. while in turnaround time we take into consideration only a single process. Throughput takes the number of processes who complete their execution in unit time, in defined time, while turnaround time, how much time your CPU takes to complete only a one process or a single process. So we now need to select an algorithm which reduces the turnaround time, as it has to complete execution of a single process in less possible time. The next criteria is the wait time. What is now the wait time? It is the amount of time a process has been waiting in the ready queue. As I had told you earlier, that waiting state is observed at different places within the system, but some waiting is known as active waiting while others are passive waiting. For example, we had seen waiting in case of blocked state, when process used to go to some device, that was also waiting, and we had also termed it as blocking. Process is waiting in ready queue is also waiting, sort of waiting, while when we swap out a process, or the state that we had discussed when a process is temporarily taken out, which we had called it as suspended, that is again a waiting state. But suspension is passive waiting, while waiting in the ready state is active waiting. So here we have to take into consideration the waiting time of a process only when it is in the ready queue, not on the devices when it was blocked and not on the suspension state. So waiting state is the active waiting when the process has spent time within the ready queue. How much time it is going to spend in the ready queue? This time is known as the wait time. Now, if an algorithm reduces the wait time, if a process waits a lot in ready queue, so such algorithm is not efficient. If an algorithm reduces the wait time of the process, that means such algorithm is quite efficient. The fifth criteria is the response time. Now, what is the response time? It is the amount to take from when a request was submitted until the first response is generated from the system. That means when you had given your process to the processor, so what was the first response generated from the system? That may not be the output, that can be some error message, that can be some IO request. So what was the first response from the system, or in how much time that response has been generated from the system? This time is known as the response time. That may not be the final output. It can be some error message, it can be some request such as IO request or some file request, whatever the first response is generated. So in how much time the first response is generated when the process has been submitted to the system, so that time is known as the response time. The time it is taken by the system to generate first response to a process when it was submitted to CPU. So these are 5 different criteria on the basis of which we select a CPU scheduling algorithm. CPU utilization, we have to keep the CPU as much busy as possible, as it is the main requirement for the multi-programmed system. The throughput should be there. Throughput is the number of processes that complete the execution in a defined unit time. Turnaround time is taken into consideration, which is the amount of time to execute a single process. Wait time is taken into consideration, which is actually the amount of time a process is waiting for its turn to be assigned to CPU within the ready queue, not on any device or not on the suspension state. The next time is the response time, or the next criteria is the response time. It is the response the time during which the first response is generated by the system when a process is assigned to CPU. That can be some error message, that can be some request, that may not be the final output. So these are the 5 CPU scheduling criteria on the basis of which we design CPU scheduling algorithms. Now we have to have an optimization criteria on the basis of which we choose a particular algorithm. Which criteria? We had already discussed the 5 different criteria. So which criteria should be maximized and which should be minimized? So here you can see 5 different criteria we had discussed in previous slide. So CPU utilization, we need to keep the system busy as much as possible. That means the CPU utilization should be maximum. The more you keep your system busy, the more you keep your CPU processor busy, the more efficient your system is. The next criteria was throughput. Throughput was the number of processes completed in defined unit time. So that means the more processes are completed in less amount of time, the more efficient, the more performance of your system will be better. So throughput need to be maximized. Third criteria is turnaround time. Turnaround time was the time for a single process to complete its execution on CPU. So we would require that a single process should be completed as soon as possible. That means the turnaround time should be minimum. A process should take less time to complete its execution. Fourth criteria is the wait time. Wait time was the amount of time a process has been waiting in the ready queue for CPU. So we would like a process to have less wait time in order to get more chance on CPU so that it completes its execution as soon as possible. So we have to minimize the wait time. We need to keep a process waiting in the ready queue for short durations. So wait time need to be minimized. The fifth criteria was the response time. What was the response time? It is the time when system generates its initial or first response when the process has been submitted to CPU. So we would like to have quick responses from the system. As soon as you assign a process to the processor, you expect quick responses from your system. That means response time should be minimized. A quick response is expected. A delayed response will reduce the performance or efficiency of your system. So here 5 criteria have been optimized. 2 among them should be kept maximum, while rest of the 3 should be minimized. CPU utilization should be maximum. Your CPU should be 100%, if not 100%, should be as much busy as possible. As you know, 100% ideal machine is not possible to be built by human. The second criteria, throughput, number of processes completed per unit time should be maximum. More processes should be completed in less amount of time, while the 3 other, which were turnaround time, wait time and response time, these 3 criteria should be minimized in order to have a good selection of CPU scheduling algorithm which can enhance the performance of your system. That is all for now. In today's discussion, we started a new chapter, CPU scheduling, and discussed some basic concepts related to CPU scheduling. We revised some basic concepts which we had already discussed in previous lectures. We discussed Again, what is CPU scheduler? The one which actually organizes the ready queue or shuffles the ready queue and changes the location of processes within the ready queue. So the process which is to be executed next on CPU is placed at the top of the ready queue, and the process which are to be executed later are placed at the bottom of or the tail of the ready queue, and this placement is actually done by the CPU scheduler. Scheduling is of two types. Either scheduling is preemptive or it is non-preemptive. In preemptive scheduling, a running process is preempted, that means interrupted, stopped in the middle. CPU is taken from it and assigned to some other process within the ready queue. This sort of scheduling is known as preemptive scheduling. So CPU scheduling can be preemptive when we can stop a running process in between, in the middle of its execution, and take CPU from it. While scheduling can be non-preemptive when a running process cannot be stopped in the middle and CPU cannot be taken away from it by force unless or until the process completes its execution on CPU and leaves the processor itself. So scheduling can be preemptive or it can be non-preemptive. So the algorithms which we will be discussing in the next lecture, so those algorithms, some of them are preemptive while some of them are non-preemptive. How they are preemptive, how they are non-preemptive, we'll be discussing them with examples and diagrams. Then we discussed what is a dispatcher. Dispatcher is actually a function or a module of operating system that dispatches a process. Dispatches means that assigns a CPU to the process. Which process? That particular process that has been selected by the CPU scheduler. So that process is generally placed at the top of the ready queue. So dispatcher selects the process from the top of the ready queue and sends it to CPU. So that process then gets executing on CPU. We then discussed different criteria for CPU scheduling. 5 different criteria have been discussed, which were CPU utilization, throughput, turnaround time, wait time, and response time. We had detailed discussion on what are these and which criteria should be minimized and which should be maximized had been discussed in detail. We'll continue our discussion within this chapter and we'll see different scheduling algorithms and we'll use those criteria to observe the efficiency and performance of different CPU scheduling algorithms with suitable examples. That is all for now. I hope the things that we have discussed today must be clear to you. I thank you all.